The loss is the squared difference, prediction minus target, squared. The derivative is simply 2 times prediction minus target. That's 2 times 0.82 minus 1.0 minus negative 0.36. The negative sign means increasing the output would decrease the loss. Good, we want the output to be higher. Step 2. How does the output change with respect to the weighted sum before the activation? This is the derivative of the sigmoid function. For sigmoid, it's output times 1 minus output. That's 0.82 times 0.18 minus 0.1476. Step 3. How does the weighted sum change with respect to a specific weight? That's just the input that weight is connected to, the activation from the previous layer. Let's say that was 0.69. Now we multiply the chain. Negative 0.36 times 0.1476 times 0.69 minus 0.0367. That number is the gradient for this weight. It tells us this weight should increase, because increasing it will reduce the loss. The magnitude tells us by how much. Now that we have the gradient, we update the weight. The rule is simple. New weight equals old weight minus learning rate times gradient. The learning rate is a small number. Let's say our learning rate is 0.1. The old weight was 0.5. The gradient was negative 0.0367. New weight equals 0.5 minus 0.1 times negative 0.0367 equals 0.5 plus 0.00367 equals 0.50367. The weight went up, just a tiny bit, and that tiny nudge makes the network's output slightly closer to the correct answer. Now imagine doing this for every single weight in the network. Hundreds, thousands, millions. Every weight gets its own gradient. Every weight gets nudged. That's one step of training. And then you do it again, and again, thousands of times. Each time, the loss gets a little smaller. The predictions get a little better. The network learns. So the full training loop looks like this. 1. Forward pass. Feed data in, get a prediction. 2. Compute the loss. How wrong were we? 3. Backward pass. Backpropagate the error. Compute gradients for every weight. 4. Update weights. Use gradient descent to nudge each weight. 5. Repeat. Next batch of data. Thousands of iterations. This loop, forward, loss, backward, update, is the heartbeat of every neural network ever trained. GPT, DALL-E, AlphaFold, self-driving cars, all of them learn this way. The architecture changes, the data changes, the scale changes, but the core algorithm? Backpropagation and gradient descent, every single time. Here's one more way to think about it. Imagine you're standing on a hilly landscape in thick fog. You can't see the bottom of the valley. You can only feel the slope under your feet. Gradient descent says, take a step downhill, feel the slope again. Take another step. Keep going until you reach the lowest point, the minimum loss. Each weight in the network is one dimension of that landscape. A network with 1,000,000 weights means a 1,000,000-dimensional landscape. You can't picture it, but the math works exactly the same. And backpropagation? That's how you feel the slope. It computes the direction of steepest descent, so gradient descent knows which way to step. That's backpropagation, the algorithm that teaches machines to learn. Next video, we'll go deeper, inside a transformer, and see how the attention mechanism actually works. That's the architecture behind GPT, Claude, and every modern language model. If this helped, subscribe so you don't miss it. And drop a comment. What algorithm should we visualize next?